Hey there, Mr. Weaver here. This is Module 5, Lessons 3 and 5 combined, Scatter plots and lines of fit, and linear regression. After this lesson, you need to be able to categorize the correlation of a set of data in a scatter plot, make and evaluate predictions by fitting linear functions to sets of data, and write equations of best fit lines using linear regressions. We went through this information in lesson 3-4, but we're going to quick look at it again. So here we have scatter plots and we are given some correlations. Again, remember, if the trend is going upward, it's a positive correlation. If the trend is going downward, it's a negative correlation. If there is no real trend and you can't tell, then there's no correlation. For more information on this, go back to lesson 4 of this module. In this lesson, we're going to use those same scatter plots, but we're going to do lines of fit. So let's learn lines of fit. A line of fit is used to describe the trend of the data in a scatter plot. So our key concept here, using a linear function to model data. First, if it's not already a scatter plot, we need to turn it into a scatter plot, plot each point, and determine if there's a relation. Then, we're going to draw a line. For this line, we're going to make it as close to the data as we can. So it goes through the middle with the other dots that don't exactly go through the line evenly spread on each side. Third, we're going to use that line to write an equation. We'll find the slope of that line and use a point or two on that line to make our equation. And finally, once we know what equation to use, we can make prediction for data that is not on the scatter plot. So looking at this same page as before, if we were to make a line of best fit through that positive correlation, we can see it has a positive slope. The line is going upward. And if you notice, I made it go approximately through the middle of the dots, where it's pretty evenly spread on each side. Same with a negative correlation. It's sloping downward and the dots are evenly spread on each side of that line. For the no correlation, I don't necessarily know where I could put my line. You'll have a hard time figuring out where to put your line. Or if you can, it'll either be a vertical line or a horizontal line, which isn't really showing any trends. Within lines of fit, when we're predicting data, there are two types of predictions. So first, there is linear extrapolation, which is using your equation to predict values outside the range of data, so off the scatter plot. There's also linear interpolation, which is using the equation to predict values that weren't given to you, but are within the range of the scatter plot. So they're just not there. Example 2, write an equation for a line of fit. Our real context here is boats. The table shows the average cost of a jet boat in the years after 2000. Write an equation to represent the data, then use the equation to predict the cost of a jet boat in 2005 and 2025. So given our table, years since 2000, so 0 years, this means it's the year 2000. 1 year, this is the year 2001. 2002, and so on. We can see that the 5 is missing. So there's our 2005. We have to predict that value. And then 2025 would be 25 years. So we need to know at 25 years what that value should be. So to figure these values out, we got to follow our steps. So first, step 1 is to make a scatter plot. So we took all the data that was here and plotted those values. In the x-axis, we have the year since 2000, and then in the y-axis, we have our cost in dollars. Then we need to draw a line of fit. So here, their line of fit they drew, I might have drawn it a little bit lower to make it better go through the dots. However, this is what they gave us, so that's what we're going to use. We can see it has a positive correlation here. It is going in an upward direction. Now we can write an equation. So they chose some points that are on the line, and they're going to use those points to figure out the slope. So remember, the slope formula, we subtract the y-coordinates and then divide it by subtracting the x-coordinates. Make sure you go in the same order. When we do that, the difference in the y coordinates, it went up 7,644, and it took 5 years to do that, or about 1,528.8 per year. Then once we know our slope, we can plug values in to our slope-intercept form to figure out our y-intercept like we've done in previous lessons. So plugging in our slope, plugging in one of the coordinates, we can calculate out b, or the starting value in the year 2000 was 17,464. Writing in a slope-intercept, that is our equation. Finally, we can use it to predict. So if we want to know after a certain amount of years, first 2000 is after 5 years, so I would plug in 5 for x, and I would calculate out my total. Then if we want to know for 25 years, so extrapolating the data, since it's outside of our range, we would plug in, instead of 5 like last time, we're going to plug in 25. Then when we calculate it out, we would get about 55,684. So our prediction in 2025, the cost of that jet boat would be about $55,684. And that is an estimate based on our line, not necessarily what it will be. Check your understanding. Our context of animals, the data shows the amount of milk that a baby goat needs by its weight. Given the data here, they already plotted it for you, and they tell you which points to use. So using those 2 points, write an equation for the line and slope intercept form. Just do this part for now. Pause the video and complete the check. Check your answer. You should have said your equation in slope intercept form is y equals 1.5x plus 5. The y value went up 60 compared to the x values of 40. So 60 divided by 40 is 1.5. Then using one of those points, plugging it in, you would find that the y-intercept would be 5. Now for part B, using that equation that we just found in part A, how much milk would be needed for a 17-pound goat and a 55-pound goat? Pause the video again and complete this part of the check. Check your answers again. A 17-pound goat would be about 30.5 ounces, where a 55-pound goat would be 87.5. Now that we know a little bit about best fit lines, let's learn about linear regression and best fit lines. We can use a calculator to find the line that most closely approximates the data in a scatter plot, or our best fit line. Linear regression is one way we can use to find a precise line of fit for a set of data. We can also use calculators to compute a number R called the correlation coefficient. That number tells you how well the data are modeled by a linear equation. So it will tell you if the correlation is positive or negative and how closely whatever equation we came up with models the data. The closer that number is to 1 or -1, then the closer the equation fits the data. So for example, if we have a weak correlation, here they're saying the R value is about 0.02. It's pretty close to 0. That tells you that it's weak. In fact, anything that is below 0.5, either positive or negative, that absolute value symbol there. So if it's a negative value between 0 and 0.5, or a positive value between 0 and 0.5, those are considered weak correlations. If the correlation coefficient is between 0.5 and 0.8, so again, either positive or negative, it's considered a moderate correlation. And then if the value is greater than 0.8, so closer to 1 or -1, then those are considered strong correlations. Example 1, find a best fit line. The table shows Jackie Robinson's total hits during each season of his major league career. Use a graphing calculator to write an equation for the best fit line for the data, then find and interpret the correlation coefficient. Here we're given the years and all of his hits. For this, we are going to use Desmos instead of our graphing calculator. So the examples and pictures in your notes are not necessarily going to match. Please learn how to do this on Desmos. We have 3 steps. First, create a table and enter the data. Then, in the next line, we're going to type in, it's essentially our slope-intercept format, except we have to make sure we have this little 1 for y1, and then a little 1 for x1. And instead of equals, we're going to use a tilde. So that's telling us that it's about equal to, giving us our best fit line, because it's a prediction. Then it's going to pop up some data for us, and we need to interpret what it means. In Desmos, we're going to add the plus sign, create a table. Once we added our table, we can start typing in our values. Instead of typing in the years, 1945, 1946, I'm going to say 1945 was year 0, and I'm going to type it in from there. So year 9 was at 98. Because remember, our scale, we can just say the years since, and our data plots are going to be the same because they're still 1 apart. Instead of doing 1945 and 1946, now our data is a lot lower. So I can see here my dots. From this kind of view, because of our scale, it might look like maybe no correlation or a vertical line, but this is where linear regression comes in. So in the second line, I'm going to type in my little formula. So y1, the little tilde that's under your escape key, push shift and hold it, m x1 plus b, and as I said, some data pops up. So we can see it graphed a line for us, and it is actually going in a downward type trend. So our scale here just kind of made it look like it wasn't doing much. So if we take our data that we were given, here's what the things mean. So first, m is your slope. So our slope here was negative 10.3. B here is your y-intercept. So the start value in this equation would be about 195. Now, we know from the graph, if we have 0, it should be at 175. But based on our line, we go with this for our linear regression. Our y-intercept was about 195. And then finally, this also tells you your correlation coefficient. Make sure you pick the r equals value, not the r squared. So r equals negative 0.8. So interpreting our results, we're going to write the equation by rounding m and b. So our equation is going to be y equals negative 10.32x plus, and then our y-intercept was 195.22. The correlation coefficient, negative 0.8022. We could have rounded that off, but because that value is above 0.8, then it models the data well. So every year, his total of hits was decreasing. And we can see that too because our slope is negative and the correlation coefficient is negative. Check your understanding. Read through the situation and the data table to create a linear regression best fit line using Desmos. Pause the video now and complete the check. Check your answer. For part A, our equation would be y equals negative 1.20x plus 62.47. Make sure you have 2 decimal places because it does say round to the nearest hundredth. For B, the correlation coefficient, the R value is negative 0.41. And then does that equation model the data well? We would say no. 0.41 falls into that weak correlation range, so it is not modeling it very well. Example 2, using the best fit line. So here we're given another situation with shopping for online sales on Cyber Monday since 2009. We want to estimate the sales in 2025. So we're going to do like we just did and use Desmos. I'm not going to go through the process again. I already typed in to Desmos and was given our linear regression data. So our correlation coefficient, 0.9935, our slope about 254.5, and our y-intercept about 778.5. Using those linear regression values, I can say my equation is about y equals 254.51x plus 778.58, and our correlation coefficient is 0.9935. So this would model the data very well. It is very close to 1 there. In Desmos, it graphs it for you. Then, when we want to extrapolate and use our graph to predict from 2025, we can just take in our equation and plug in 16. That's because 2025 is 16 years after 2009. This one started at 2009, not 2000. Then we can look, those lines would intersect at 16, 4,851, or if you just substituted 16 into the equation, you would get about 4,851. What that would mean in this context, Cyber Monday sales would be about 4,851,000,000, because the data originally we were given was in millions. In Desmos, if we want to use our value for when x is equal to 16, we can do it one of two ways. We can type in our original equation and also type in x equals 16, and we'd have to keep zooming out until we find where they intersect. That might take a little while to do. Or we can always evaluate by changing x with parentheses to 16, and it will tell us our value at that point. So here again, 4,850.74, about 4851. Check your understanding, read through the situation, and using the data table, go into Desmos, create a linear regression to estimate the number of users in 2030. Pause the video now and complete the check. Let's check our answer using Desmos. In Desmos, if I type in my table and my equation for my linear regression, I would get the equation y is equal to 140.4x plus 379.4. Remember, this is in millions. Then, if I want to know 2030, which is 19 years after 2011, instead of x, I'm going to plug in 19, and I get 3,047. So if I come back to my choices, 3,047 is answer D. That would be 3,047 million users, or in other words, 3,047,000,000 users. So D would be our correct answer.